Hey everyone, welcome back to linear algebra. This will be part B of lecture 17. And where we left off, we had just defined what the dimension of a vector space is. And so the theorem that came right before that said that all bases of a vector space, though the elements of the basis might differ, the size of the basis is always the same. And then we use that as the no pun, so we use that as the basis for the definition of basis, or the definition of dimension. And so we're going to just expand on this a bit, and we're going to draw out some examples and look at some nice corollaries and theorems regarding dimension that really point to some really beautiful structure in the linear algebra world. So let's start with a corollary. Okay, and so for this is a nice way to think about it. It makes kind of clear some of the implications of dimension and basis size. And so let's let V be a finite dimensional vector space. Let V be a finite dimensional vector space. Okay. Then two things here. Okay, so the first one is, let's suppose S is a finite subset of V that spans V. So suppose S is a finite subset of V that spans V. Okay. So S is just some subset of V, but it happens to span V. Then what can we say about that? Then the dimension of V is going to be less than or equal to the size of S. Okay? And moreover, the size of S is equal to the dimension of V if and only if S is a basis for V. Okay, so if S is just some finite subset of V that happens to span it, then the dimension of V has to be less than or equal to S, right? There could be extra vectors in S, right? There could be extra vectors. S doesn't necessarily have to be linearly independent. But if S is linearly independent, then it automatically becomes a basis, and that's when we see that the size of S is exactly equal to the dimension of V. Okay, that makes sense, right? That should hopefully follow. The second item says that let's suppose T is a linearly independent subset of V. Okay, so now we're talking about T being a linearly independent subset of some vector space V. Then what does that mean? Well, T is finite. So T is finite, and the size of T is less than or equal to the dimension of V. Okay. Right? And just like before, we say that moreover, the size of T is equal to the dimension of V if and only if T is a basis for V. Okay, so here we've got T is a linearly independent subset of V. All that means is that all the elements in T are linearly independent. None of them can be written as a linear combination of the others. There's no redundant vectors in T. And so if that's the case, then T is automatically a smaller set than the dimension of V. Okay? It's not necessarily big enough to form a basis, but so it's less than the dimension of V, right? And if you start adding vectors to T and the T remains linearly independent, at some point the size of T will equal the dimension of V, and that happens to be the largest linearly independent set you can get inside of a vector space V that has dimension V, right? Okay. So this corollary is very beautiful. It sets up a nice, it really sets up a nice kind of bound here, right? It sets up a nice relationship between the size of a linearly independent set and the size of a spanning set, right? So what does it show? First of all, okay, this is separate here. This is commentary at this point. So what this basically says is that a large enough, oh, hold on a second, sorry about that. It says that a large enough, right, a large enough linearly independent set is a basis. Okay, it's easy to get a single vector is linearly independent, but it's not a basis for most things. Two, it's not hard to find two vectors that happen to be linearly independent, but it may not be a basis yet. It's as the linearly independent set grows, it becomes a basis, and it can't get any larger at that point. Okay, so a large enough linearly independent set is a basis, and it also shows, right, that a small enough spanning set is a basis, right? So the flip side here is that, hey, look, it's real easy to get a spanning set if I put 1,000,000 vectors in it, right? It's easy to find a spanning set for R3 if I have 1,000,000 vectors in my subset. No problem. But obviously, I've got a lot of redundancy, so I start reducing. I start throwing out the redundant vectors, right? So at a certain point, I've thrown out all the vectors I can throw out while still remaining spanning a spanning set, right? And once I've done that, I have a basis, right? So a large enough linearly independent set is a basis. A small enough spanning set is a basis. So there's like this borderline number between these two, right? So the borderline size is the dimension of the vector space. Right? If your linearly independent set is smaller than the dimension, then it's not a basis. If your spanning set is larger than the dimension, it's not a basis. It's only when they're exactly the same, right? You have this perfect, like, balance. Okay. All right. Excellent. So that's got a nice idea. It's got a nice ring to it. It feels right. It's aesthetically pleasing, right? I think so. Next, theorem. So in this theorem, we're just gonna continue to expand along this idea of spanning sets, bases, and dimension. So let's let V be a vector space. Okay, with a spanning set S. Okay, and just keep in mind that all that means is that the span of S equals V. Okay. Okay. We're going to let B be a maximally linearly independent subset of S. Okay. All right, so I've got a vector space V, and I've got some subset of V that spans V. And all I'm saying is let's take B to be some linearly independent subset of S. Okay, so if I, have some subset of S, it's linearly independent, but it's maximally linearly independent. That's the key, right? Meaning, what do we mean when we say it's maximally linearly independent? Basically means if I put one more vector in there, no matter which vector it is, it's automatically, the set becomes dependent. You can't add even one more linearly independent vector to the set. It's maximal. Okay, so let B be a maximally linearly independent subset of S, then B is a basis for V. Okay. Right? And so this is just, you start with a spanning set, you can shrink it down to a basis pretty easily. Okay, let's take an example of this. That's the idea here. You start with a spanning set, you can shrink it down and get to a basis. Right? And that basis can be found by just shrinking it down to a maximally linearly independent subset. Let's do an example of this, kind of a simple example. But you can see the idea easy in the example. So let's let S equal, 1, -2, 1, 3, 1, -2, 5, -3, 0, 5, 4, -5. So we're kind of putting a lot of them in here, and 0, 0, 0. So this is a subset of R3. Okay, so I've got 5 vectors here. And let's let B be a subset of S where, B is equal to, we'll just grab the first couple. So we'll grab 1, -2, 1, and 5, -3, 0. Let's kind of jump over that one. Okay, so this is a subset of S, right? Well, the thing to notice here is that the other 3, so S may span R3. Oh, sorry, no, it doesn't span R3. So the thing to notice here is that the 3 vectors that we didn't choose to be in B can be written as linear combinations of the 2 we did choose, right? So notice that the other 3 can be written as, well, so kind of start with the 3, 1, -2 here. That's equal to -2 times this first vector, 1, -2, 1, plus 1 times the second one. All right, so take a second to confirm that, but make sure you can see where that's coming from. And then this guy down here, 5, 4, -5, that's equal to -5 times the first one, plus 2 times the second. Okay, so this one and that one can both be written as linear combinations, these other 2. And obviously the 0, 0, 0 can as well, right? That's just 0 times each of the others, right? And so it looks like that. Okay. Okay. So B is what we call maximally linearly independent. So B is a maximally linearly independent subset of S. Okay. And that being the case, it's a basis for the span of S. It's a basis for the span of S. Okay, so this set S has 5 elements in it, and we can identify the span of it, right? As all vectors that can be written as linear combinations of these 5 vectors. Well, it turns out that 3 of the 5, right, the 3 that I've marked here, are all redundant. Those 3 can be written as combinations of these 2, right? So B is the maximal linear independent subset here. And so B is a basis for the span of S, right? So any vector that can be written using all of S can also be written using all of B, just B, the 2 elements in B. Okay, so any vector that can be expressed using S can also be expressed using just B. Okay, and so that makes B a basis for the span of S. Okay, very good, very good. Next theorem. Okay, so these are all, this is going to be kind of the flip side of that previous one. So let's let V be a vector space and let B be a minimal spanning set for V. Let's let B be a minimal spanning set for V. Then B is a basis for V. B is a basis for V. Okay, makes sense, right? So, you know, as I said, there's lots of, you know, I can easily generate a spanning set for R3 by grabbing a million random vectors from R3. But I don't have a basis because there's a ton of redundancy in there, right? So I have to start removing vectors from that set. And at a certain point, I'm going to get to what's called the minimal spanning set. And when I do that, when I get to the minimal spanning set, I'll have a basis. Okay. All right. And so that's kind of just the same idea as what we had before, but kind of in reverse. Okay. All right, and let's do one last theorem here. One last theorem. And this one has to do with when can I infer that a vector space is finite dimensional, and what does that tell me about that vector spaces and the subspaces in particular inside of it. All right, so let's let V be a finite dimensional vector space. We'll let V be a finite dimensional vector space, and let W be a subspace of V. Okay. So, I mean, simple setup. You got a finite dimensional vector space and a subspace, right? Then W is also finite dimensional. So W is also finite dimensional with specifically the dimension of W less than or equal to the dimension of V. Okay, so that's nice. That's how you'd hope it would work. If I've got a vector space V, it's going to have a dimension. If I got another subspace, which is just a smaller, you know, in kind of intuitively smaller vector space, it's also going to have a dimension. You'd like the dimensions to be nested in the same manner, and that appears to be the case. And moreover, right, it does say less than or equal to, and moreover, the dimension of W is going to be equal to the dimension of V if and only if W equals V, i.e. you're talking about the same thing, right? The subspace is the same as the vector space. That's great. That's like exactly how you'd want this to look. You wouldn't want it to be otherwise, right? It wouldn't seem right if you had a proper subset of a vector space V, if you had a subspace that was a proper subset of V and yet had the same dimension, right? You would hope that if it truly is a subset, like a proper subset, if W truly is a proper subset of V, then you'd hope the dimension would be different, like less than in particular. And that is the case. That is the case. You only have equivalent dimension if the subspace is actually the same as the vector space, which is exactly what you want to see. Okay. Okay. And so there's lots of examples of this. Let's do one with polynomials just real quick here. If I consider P3 and P4. Okay, so we know that B of P3, a basis for P3 would be 1x, x squared, x cubed. Oh, wrote that in the wrong spot there. All right, I'm just going to start over on that one. A basis for P3 is equal to 1x, x squared, x cubed, right? All third degree or smaller polynomials. That's P3, and this is a basis for it. A basis for P4 is 1x, x squared, x cubed, x to the fourth. These are the standard bases for these things. And so this implies that the dimension of P3 is equal to 4, and the dimension of P4 is equal to 5. 1, 2, 3, 4, 5 elements in the basis. So we can see that, you know, P3 is a proper subset of P4, right? This has got fourth degree polynomials. This doesn't, right? So there are fewer things here than there are here. There are elements here that aren't here, right? So P3 is a subset of P4, proper subset, and we see that the dimension of P3 is less than or equal to the dimension of P4, as the theorem would indicate. Right? We can just see it in this example really clearly. Okay. Here's kind of a nice, this idea of dimension is a key concept in linear algebra. So let's talk through, this is kind of a nice high level, grand sort of example. Let's consider the nested sequence of subspaces of R3. So consider the nested sequence of subspaces of the vector space R3. Okay, so we'll start with the kind of the core subspace here, and that's just the 0 vector. Okay, what's the dimension here? Dimension 0. Let's move up a level and talk about the subspace here of R3 that is, just take any arbitrary vector and find all the scalar multiples of it. So I'm going to write it like this: scalar multiples of 121, whatever that happens to be. Right, just a random vector. Okay, so clearly this is a subset of this, proper subset. We can make this a proper subset of something like the xy plane, which is a subspace. It's a vector space, right? And the xy plane is a nice subset of R3 itself. Right? These are you can think of this as vectors where the z component, the k component, is all 0, right? You're always on the plane then. Okay, but these can all be written as R3 vectors or 3 vectors. And so it's a subset of R3, right? And so what are the dimensions? Here you got the dimension is 0, the dimension here is 1, the dimension here is 2, and the dimension here is 3. And this is all just based on the idea of the basis, right? It just takes one vector to form a basis here, namely 1, 2, 1 is the basis. Here, I and j with zeros added onto them for the third component form a basis for a xy plane, and then the standard basis for R3, right? 3 elements, 2 elements, 1 element, 0 elements. Right, so you can see this nice nesting of the dimensions. Right, so 0 less than 1, less than 2, less than 3, obviously. Okay, so that's kind of a nice idea. Okay. All right. So I think we'll leave it there for this section. And so again, we introduced the idea of a basis here and talked about how that concept of a basis leads to the idea of a dimension of a vector space. And so in the next section, we'll talk through how to construct bases. There's a number of methods. It'll be a little more of a pragmatic sort of section on how to actually calculate a basis, how to quickly find a basis given a couple of linear independent vectors. How can we expand them easily to form a basis? And so we'll need to be able to do that to do some of the stuff that comes later. And so it's a really key section. So, all right, we will see you all in that next video. Take care.